Hello! Previously, we have used the best response function to find a Nash equilibrium. In this lecture, we will look at another way to find a Nash equilibrium, and that is through strict dominance. We have previously seen that the prisoner's dilemma has a strictly dominating strategy, and any player with such a strategy will play it. However, not all games have strictly dominating strategies. A more useful notion is the opposite, finding strategies that are strictly dominated by other strategies. We give some related definitions here. For two strategies SI1 and SI2 for player I, we say that SI1 strictly dominates SI2 if, for all the strategies of the other players S minus I, UI of SI1 S minus I is strictly greater than UI of SI2 S minus I. This means that the utility of player I for playing SI1 is strictly better than the utility for playing SI2, regardless of what the other players have played. Now, if there exists a strategy that strictly dominates SI, then SI is strictly dominated. On the other hand, if SI strictly dominates all strategies for player I except for itself, then SI is a strictly dominating strategy. In Prisoner's Dilemma, steal is a strictly dominating strategy for both players, as playing steal is strictly better than playing share regardless of what the other player has played. We now write down our intuition about strictly dominating strategies in this lemma. If SI is a strictly dominating strategy for player I and S star is a Nash equilibrium, then SI star is equal to SI. In other words, in any Nash equilibrium, the strictly dominating strategy is played whenever it exists. So a game is easy to play if such a strategy exists. But of course, not all games have these strategies. We now flip this around and look at strictly dominated strategies. Here is an example. Consider the two-player game with the following payoff table. There are two strategies for player 1, A and B, and three strategies for player 2, X, Y, and Z. Look at this table carefully and see if you can find any strategy that is strictly dominated by another one. We see that Z is strictly dominated by X because when player 1 plays A, playing X gives you better utility than Z, and when player 1 plays B, playing X also gives you a better utility than Z. So Z is a strictly dominated strategy. Now, if you have a strictly dominated strategy, then there is no reason to play this strategy. You just play the one that dominates it and you get a better utility. So this gives us the following lemma. If S star is a Nash equilibrium, then SI star is not strictly dominated for any player I. So no player will play a strictly dominated strategy in any Nash equilibrium. We will leave the proofs of these two lemmas as easy exercises. So now when we are searching for a Nash equilibrium, we can discount a strategy that is strictly dominated. Take a look at our example again. We see that Z is strictly dominated, so it will not appear in any Nash equilibrium. So we can eliminate Z from this table. Now we have a smaller game with two strategies each. Now in the smaller game, we see that B is a strictly dominated strategy for player 1. Now notice that B is strictly dominated in this new game and not the original game. And now we can eliminate B from this game. We are left with two strategy profiles, And it is easy to see that X is a strictly dominated strategy. Eliminating X leaves us with just one strategy profile, AY. And we claim that this is a Nash equilibrium for the game. You can double check that this is indeed the case going back to the original payoff table. So this process is called iterated elimination of strictly dominated strategies, or IESDS. We repeatedly eliminate strictly dominated strategies until we have only one strategy profile. We claim that if this works, then the surviving profile is the unique Nash equilibrium of the game. We will give a sketch of the proof soon. Now this is not going to work for all strategic games. Many strategic games do not even have strictly dominated strategies. But for games where this works, we can use this process to find the only Nash equilibrium in that game. We now look at another example called the facility location game. In this game, two firms are each given a permit to open one store in one of the 6 towns along a highway. Firm 1 can open in A, C, or E. Firm 2 can open in B, D, or F. We assume that the towns are equally spaced and equally populated. Customers in one town will go to the closest store. So the question is, where to open the stores? We can write down the payoff table as follows. For example, if firm 1 opens at A and firm 2 opens at D, then A and B would be closer to A than D, so 2 towns will go to A. C, D, E, F are all closer to D than A, so they will go to D. So the payoff here is 2 and 4. Now, can you find any strictly dominated strategies here? Well, for firm 1, A is strictly dominated by C. We can check their payoffs. For firm 2, F is strictly dominated by D. We can now eliminate these 2 strategies to get this smaller game with 2 strategies each. Here, for firm 1, E is strictly dominated by C, and for firm 2, B is strictly dominated by D. We can now eliminate these 2 strategies, and we end up with just one strategy profile, C and D. So we say that C and D is a Nash equilibrium. Note that we can extend this to any arbitrary number of towns, say 1000 towns with alternating options. The 2 ends are strictly dominated by the center towns. We can eliminate them to get 998 towns. We can then repeat until we end with the 2 towns in the center as our Nash equilibrium. We now explain why iterative elimination of strictly dominated strategies is a process that finds a Nash equilibrium if we do make it to the end. Here is the main theorem. Suppose G is a strategic game. If IESDS ends with only one strategy profile S star, then S star is the unique Nash equilibrium of G. And this theorem is a direct consequence of the following result. Let G be a strategic game where SI is a strictly dominated strategy for player I. Let G' be obtained from G by removing SI from the strategy set for player I. Then, S star is a Nash equilibrium of G if and only if S star is a Nash equilibrium of G'. We now give a sketch of the proof here. For the forward direction, we suppose that S star is a Nash equilibrium of G. We want to prove that S star is a Nash equilibrium of G', But G prime is a restriction of G, so we need to first establish that S star is a valid strategy profile in G prime. Can you see why that is? Since Si is strictly dominated in G, it cannot appear as a strategy in the Nash equilibrium of G, S star. This is from our earlier lemma. So, S star is a valid strategy profile in G prime. We now suppose that S star is not a Nash equilibrium of G prime. Can you find a contradiction here? If S star is not a Nash equilibrium of G prime, then a player can deviate from their own strategy to get a higher utility. However, all strategies in G prime are available in G, so such a player can do it in G as well. So this contradicts the fact that S star is a Nash equilibrium of G. For the reverse direction, we suppose that S star is a Nash equilibrium of G prime. We know that S star is certainly a strategy profile for G, so suppose that S star is not a Nash equilibrium in G. Then a certain player can deviate from their own strategy to get a higher utility. Now can this player do the same thing in G prime as well? If this deviation can be replicated in G prime, that will result in a contradiction that S star is a Nash equilibrium of G prime. But there is one possible way of doing this without causing this contradiction, and that is if player I switches to strategy Si, which is the only strategy in G that is not in G prime. So now, can you find a contradiction here? Now Si is a strictly dominated strategy. So player I could switch to the strategy that strictly dominates Si, which is available in G prime. And that will give the player a higher utility in G prime. This contradicts the fact that S star is a Nash equilibrium in G prime. And that completes our proof sketch. We will leave the formal proof of this and the proof that this implies IESDS produces a unique Nash equilibrium as exercises. In the next lecture, we will explore a similar idea to strict dominance with weak dominance.